Hey everybody, so in this video I'm going to be talking about a little intro about rotational kinematics, or you can think of it as rotational dynamics, the motion involving the rotation of objects uh, about a fixed point. So for example, a gear, like right here, this gear turning, okay, about this fixed point. Okay, so you remember these kinematic equations when you're dealing with constant acceleration. Uh, okay, so in rotational kinematics, you have the same exact thing for constant acceleration, but with a little change of variables. So instead of position, okay, we denote it with x. It could be the position in x, in the x direction, or position in y direction. Is the same here in this case, but it's now theta. Okay, so let's say here we start, okay, at time equals 0, and we start rotating that way. So here's your initial theta, and then let's say our final theta is right here at 90 degrees. Okay, so we're just going to turn this entire thing and then stop right here. Okay, so your initial theta would be 0 degrees, and your final theta would be 90 degrees in this case. So that's instead of position or the position of rotational kinematics is the same as theta, is basically the theta. Okay, so and then your velocity, instead of having v, now we have angular velocity, which is denoted with lowercase omega, and instead of this acceleration in rectangular motion, now we have angular acceleration and rotational kinematics. Oops, where'd this come from? Okay, and then time stays the same. Time is still in the same domain, so we stick with time with the variable t. Okay, so that's only when you're dealing with constant acceleration, keep that in mind. So let's move down right here. So I'm going to talk about the relationship of these three gears, how their motion is related. So if we are spinning, all these gears are connected to this rod, and this rod is going to be spinning in this direction, okay, counterclockwise. Okay, all of them are going to be spinning in the counterclockwise direction, but these concentric gears, they're going to have the same angular velocity, okay, the angular motion, or or also the same angular acceleration. Okay, all these concentric gears, they're gonna have the same angular motion. So let's say we're spinning this rod, okay, right here, we're spinning it with an angular velocity of 5 radians per second. Okay, this one's gonna have an angular velocity of 5 radians per second. This is also gonna have 5 radians. This is also gonna have 5 radians per second. But the only thing different is their tangential velocity. Okay, so we're in 3D right here. So let's say we have a 3D vector coming in like that. Okay, the tangential velocity. Okay, their tangential velocity is not going to be the same, and the way we relate that tangential velocity is v is equal to omega r. So if omega is constant amongst all of these three gears, but what's changing is the radius. So if we have radius here of 2 centimeters, here we have 5 centimeters, here we have 10 centimeters. Okay, you're going to be multiplying these, the omega, the 5 radians per second by their radius, and the larger the radius, okay, you're going to have a larger tangential velocity. Now moving on right here, okay, to the right, I have these two gears, okay, right here. These two gears, let's say this larger gear rotates, okay, at 5 radians per second. Okay, so it's going to have a tangential velocity right here. Okay, tangential velocity same, and tangential velocity right here, and so on. When it hits this smaller gear right here, okay, oh my gosh, what's going on? What's going on? It's not me. What is this? Okay. All right. So when this gear right here, when it's hit by that moving the other larger gear, okay, this lower gear is going to have the same tangential velocity because they both hit each other right there and it's going to cause this smaller gear to spin at the same rate, but its tangential velocity is going to be the same. But what's different here, okay, they're not concentric as opposed to this. So what's happening here is that they're going to have different angular velocities. So let's say we don't know what the angular velocity here is. We don't know its tangential velocity, but we know the tangential velocity of this larger gear is 5 meters per second. Okay, this is tangential, not angular. And let's say its radius, it has a radius of 10 meters, and this smaller one has a radius of 3 meters. So the way we could translate the information we have in this larger gear to this gear, okay, we know that the tangential velocity of both of them is going to be the same. Okay, so now that we know that the tangential velocity right here is 5 meters per second, this smaller gear is going to have a tangential velocity of 5 meters per second, but 4 times the angular velocity, and we know this formula, okay, is divided by r on both sides, and then so its angular velocity is going to be 5, tangential divided by 3, and that will give you the angular velocity. And so to summarize, if you have these two coplanar gears, right, they hit each other at the same, this point right here, they're going to have the same tangential velocity but not the same angular velocity. But if you have concentric circles that are connected by some moving force, something that's moving them, they're all connected to the same rod, okay, it doesn't matter that, see, they're on different planes right here. This is a different plane, but they're all concentric. Okay, they're all going to have the same angular velocity, but not the same tangential velocity. And that's a little intro, the big picture of how rotational kinematics really works.